Ladies and gentlemen, bonjour. So I am very pleased to speak here as a Stanford graduate in front of MIT technology. That's very interesting. So here in Toulouse, welcome to all of you. Welcome in Europe, welcome in France, and welcome in Toulouse. Toulouse, the capital of space. We are more than 12,000 people working in the space domain. 12,000 people. Where is my, okay, I need something. So, and what do? We design, we build satellites, we operate satellites, but we don't build launchers. So we are not SpaceX competitor in Toulouse. And what we do in industry, in scientific laboratories, and in CNES. Very often, we have technology in space, and the technology in space is in a very difficult environment. The environment in space is vacuum, thermal. On one side, when you have the sun, is 150 degrees Celsius. On the other side is minus 150 Celsius. So thermal control is very important. When you see also we have radiation in space. We have radiation, and radiation is very, very important. We are protected on the Earth due to the magnetosphere and the atmosphere itself. But in space, we have radiation. And you will see that the next technology, maybe we'll have problem on the Earth itself. We'll see that. The other point is the fact that in orbit, when you launch something, it's not possible to repair it. It's not very easy to make a reset. But so the only way to work is to have something with a lot of digital technology inside. So everything in space is digital. Everything is Wi-Fi since the beginning. So we work on this since, let's say, more than 50 years. So I will show you some example of what we have done, sometime here in Toulouse, sometime with others, because the space activity is not a French activity. It's going to cooperation with a lot of people, with a lot of countries, and only in CNES, we have 40 programs in parallel working with more than 20 countries in the world. So that means that we are fully international. The first thing I want to show you, that something you know very well known, is Mars. We go on Mars because Mars is a planet on our system, and we want to understand exactly the past of Mars. And this rover is done by US, the GPL people, and we build the laser on it. And the laser on it is something that is a megawatt in 5 microseconds, and we put all in rocks in order to analyze the composition of the rocks. And this is, we make all on Mars. That's our story. So on this rock, you can see on the before and after. So we put marks on Mars. What we discovered, the scientists discovered that Mars has water. And now we are sure that Mars has water. And the water is at pH 7. It's a drinkable water. We have found drinkable water on Mars. So 10 years ago, we didn't know that. So now we change the way we understand our planet, and we change the way we understand our solar system. And we also change the way we understand our galaxy, but that's another story. Next technology we use technology in order to monitor the Earth. So we put satellite above the ocean, and we check with a radar the height between the satellite and the water. It seems to be easy with the radar. But we go through ionosphere, we go through a lot of things in the atmosphere. The satellite is as 1,000 kilometers high, so it's 2,000 way, both ways. And we have to check the exact altitude. So we have to know exactly what is the orbit. We have to know exactly what is the geoid of the Earth. That means where are the mass distributed around the Earth. And we say, since 92, that the sea level ramp up of 7 centimeters, the average on the Earth. These kind of curves had been given to COP21 in Paris in order to say that there is a global warming. And that's very important to have all technology inside. It's impossible to say to everybody that the Earth is warming if we have a problem in a drift in a clock in orbit. So we have to check everything in orbit. So that's very difficult in terms of technology, let's say. One adventure we had in Europe, it's what we call Rosetta Philae. You all understand about that. It was a wonderful story. It ended last week because we put the two vehicles on the comet. The comet is a smart material. It's very interesting because we discovered everything. We thought that it was ice. It was not ice at all. It was a lot of things, but not only ice. So that's very interesting to see that the technology we put on that, the technology of the last century, it spent 10 years to go to the comet, and now it works at the end of the technological story, but the beginning of the scientist story, because they only check 5% of the data. So we have a lot of data coming from that. This image is a very strange image, because it's a very small satellite close to the International Space Station. What we have, this close satellite is 10 centimeter cube. And the International Space Station is larger than a stadium. So that's not at all the same technology we use in there. So it's very interesting to see that the technology we have to use are very interesting to check, not only in space, but also in the stratosphere. Because the stratosphere is above the aircraft. It's above 12 kilometers high. And we have to check everything in this stratosphere, and we use balloon. And you know that our balloon we use for scientists is now used, I don't know why it doesn't work, it's used also by Google, because they use balloon to put that at 20 kilometers high, and we designed the balloon with them. Just go back to the technology we use. We use micro and nanotechnology. We are not at the top of the technology. The nanotechnology now is around 10 nanometers of lithography. We are around 65, but in orbit we have radiation a lot. When you will be at 10 nanometer on ground, you will see some kind of problem due to radiation, because we have radiation, not at the same level that we have in orbit. But you need, with this kind of technology is used. The other part is something we put in orbit. It's just a 3D camera. A camera, the size of is less than 2 watts, but you have better camera on your smartphone, but it doesn't work in space. We also use additive manufacturing. It's a way that it's already in orbit. It's already on satellite. We have corner plates. We have on the left-hand side, you see that this deployment mechanism is divided by 2. The mass is divided by 2, because for us, mass is very, very important, because it's very expensive to go in orbit. And on the right-hand side, you have propellant management device. It's kind of sponge inside the tank, because when you are in microgravity, the liquid is going everywhere. It's not something in the gravity, so it's going everywhere. So you need a sponge to keep it, and that's done by additive manufacturing. We put that also on telescope. We have some kind of glass on one way and carbon of silicon on the other end. It's done by industry. And the last thing that I wanted to show you is something it seems to be a machine. It's active control, thermal control. Active thermal control, because we have problem. We don't have convection in orbit. That's obvious, in vacuum. No convection. Ventilator, it doesn't work. So we need to evacuate the watts everywhere on the right side of the satellite and the vehicle. So we put these kind of things. It's with caloduc and things and a double-phase pump, and it works quite well. So, as you understand, for us, technology is everywhere, and we need to qualify the technology for space application and for the space environment. It takes months and years. And as soon as we have a qualified technology, we use it, even for 10 years. So it's not at all the time constant of a smartphone. But it's very interesting to see that each time we have a good technology, we use it, qualify it, and we go far away from the Earth. Thank you very much.